All my homies hate the Kekule model, and you need to know the reasons why the delocalized model is superior.
The first reason as to why the delocalized model is better than the Kekule model is due to the enthalpy of hydrogenation of benzene. The Kekule model, which is cyclohexatrione, is suggesting to us that there's an enthalpy of hydrogenation of minus 360 kilojoules per mole. But in reality, benzene has an enthalpy of minus 208 kilojoules per mole. So that means less energy was released in that hydrogenation of benzene. So that must mean that benzene had less energy to begin with, which must have been brought on by greater stability. And that stability is brought on by delocalization of electrons, therefore spreading a charge. That's how it became stable. So this directly contradicts what the Kekule model implies. The second reason you need to know is bromination resistance. Now, the Kekule model implies that benzene is an alkene of sorts, and we know that alkenes turn bromine water clear. That's because charge localization means there is a high electron density on that carbon double bond, and because there's a high electron density, it repels electrons in bromine, establishing dipoles, and that enables the formation of a bromine electrophile for electrophilic addition. But in reality, when we place benzene in bromine water, it does not turn clear. And so that must mean that no bromine electrophile is being formed. And that's because there's no charge localization in benzene. There's only delocalization in benzene. And so that further supports this idea of a ring of delocalization, which lowers electron density on benzene, preventing the formation of a bromine electrophile for further reaction. And so that further disproves the Kekule model because the reality of things contradicts what the Kekule model implies. The final reason as to why the Kekule model is worse than the delocalized model is to do with the bond lengths present in benzene. Now, the Kekule model implies that benzene is a mixture of carbon double bonds and carbon single bonds. But when we go to measure the bond lengths of benzene, there is only one bond length present, and that bond length is between both carbon double bonds and carbon single bonds. And so, once more, reality of things contradicts what the Kekule model should be implying. Nitration of benzene. For the nitration of benzene, you need to know the overall equation, the formation of the electrophile, the conditions, and obviously the mechanism. We know that the end product, nitration of benzene, is a nitrobenzene. So from that, I know we need this nitronium ion, NO2+, which we can get from nitric acid. So that's one of our reactants. We also know that benzene is unable to form electrophiles on its own. So we definitely need a catalyst to help produce that nitronium electrophile, which benzene will react with. To get that nitronium ion from nitric acid, I need to react nitric acid with a stronger acid. So here, it's going to be sulfuric acid. And both of these acids will be concentrated. When we react sulfuric acid with nitric acid, this nitric acid is going to be acting as a base, and the sulfuric acid is going to act as the acid. That's because sulfuric acid is a stronger acid than nitric acid. So sulfuric acid donates H+ to HNO3 and forms hydrogen sulfide. And then we're also going to form nitrooxonium. And this nitrooxonium is incredibly unstable, and it will pretty much immediately break down into water and the nitronium ion, which will be our electrophile for our reaction mechanism. In our reaction mechanism, 2 electrons from the delocalized ring of electrons will be used to form a bond to the nitronium ion. So we draw our arrow starting from the center of our delocalized ring, and I'm going to draw it through the carbon, and we end the arrow going towards the nitrogen atom, which is positively charged. Now, this causes a positive charge to be gained by the benzene, and it causes the delocalized ring to be disrupted. And we show that by drawing a horseshoe shape around the carbon atom, which bonded to the NO2. And alongside that, we give this delocalized ring a positive charge. We're also going to show the bonds to hydrogen and the bonds to the nitronium. From there, electrons move from the carbon-hydrogen bond to restore the delocalized ring. So we show that with an arrow going into our positive charge. That will then form nitrobenzene, and release H+. And that H+ will react with HSO4- to then reform the catalyst. Alternatively, you could display this in just a single equation, or you can go to the prior step and show those electrons moving towards the hydrogen. Now, what about the conditions? Well, the conditions are simple. Firstly, we want to do this below 50 degrees to prevent extra substitutions of nitronium electrophile. And we're also going to do this reaction in the presence of concentrated sulfuric acid. Once we form nitrobenzene, we can go one step further with that molecule. We can reduce it to form phenylamine. And to reduce nitrobenzene, we use tin and concentrated hydrochloric acid. And we do this while heating under reflux. And after all of that, we then add NaOH to neutralize that concentrated hydrochloric acid. So in the equation, we use brackets H to show that there's a reducing agent, and then this will obviously form phenylamine and water. Halogenation of benzene. For halogenation of benzene, you need to know the overall equation, the mechanism, the conditions, and the equation for the formation of the electrophile. I know halobenzene is being produced, so obviously a halogen is going to be needed. And I'm going to represent that with X. But in your exam, remember to be specific. And the other product that will be made is a hydrogen halide of some kind. Now, benzene we know is unable to form electrophiles on its own. So a catalyst will be needed to form a halogen electrophile. So for this catalyst, could be iron bromide, FeBr3, it could be aluminium chloride, AlCl3, or any other compounds which is a metal halide carrier. I'm going to show that with FeX3 in general terms. When the catalyst reacts with the halogen, we form a tetrahalide compound with a negative charge, and we'll also form a halogen cation. Now that halogen cation is our electrophile. Now, 2 electrons from the delocalized ring are used to form a bond with the halogen electrophile. So we draw our arrow going from the delocalized ring, and I draw it going through the carbon atom and towards that halogen cation. This will cause positive charge to be gained by the benzene and cause the delocalized ring to be disrupted. So we show this by drawing a horseshoe shape around the carbon atom which formed a bond to the halogen, and we give that a positive charge. We're also going to show the bond to the hydrogen that the carbon has and the bond to this halogen. Electrons then move from that carbon-hydrogen bond to restore the delocalized ring. So we show that with an arrow from the CH bond going into the positive charge. That will then release H+, which will then react with our metal tetrahalide to reform the catalyst. And that will then give us a hydrogen halide as well. Alternatively, you could show this in the prior step by showing the electrons going into that hydrogen atom. The conditions for this are quite simple. Absolutely want anhydrous conditions. And we should probably do this in a fume cupboard as well. Now, we want this to be anhydrous because these metal halides, particularly if we use AlCl3, will react readily with water. And so it's to prevent that reaction. We do this in a fume cupboard to mitigate the effects of toxic hydrogen halide. Because regardless of what hydrogen halide it is, whether it's hydrogen bromide, chloride, iodide, fluoride, it's going to be toxic. Now we're also obviously going to do this in the presence of our catalyst, whether that be FeBr3, AlCl3, or any other metal halide carrier. Friedel-Kraft's alkylation. Alkylation involves the addition of an alkane to the benzene. So the electrophile involved needs to be an alkyl cation. So I can deduce that a chloroalkane will be used to form that alkyl cation, simply because that CCl bond is polar, and so we can break it through a reaction to then form the cation. So a chloroalkane is going to be the reactant involved here. And for my examples, I'm going to use a primary haloalkane. Obviously, remember that benzene can't form electrophiles on its own, so once again we require a catalyst to react with this chloroalkane to form the electrophile. So for this, I'm going to use aluminium chloride. It's got the same halogen which is in our react. And finally, our other product must be hydrogen chloride. When we react the chloroalkane with aluminium chloride, chlorine is lost from the chloroalkane as a chloride ion. And that chloride ion forms a dated covalent bond with AlCl3. That will form AlCl4- and alkylation, with a positive charge lying on the carbon atom. The reaction mechanism will look like this. 2 electrons from the delocalized ring are used to form a bond with the alkyl electrophile. So we draw our arrow going from the center of our delocalized ring, and I draw it going through the carbon atom, and then we draw that going into the positively charged carbon atom of our alkyl electrophile. This causes a positive charge to be gained by the benzene, and it causes the delocalized ring to be disrupted. So we show that by drawing a horseshoe shape around the carbon atom which formed the bond to the alkyl electrophile, and we give that a positive charge. And we're also going to show bonds that this carbon has to hydrogen and that alkyl electrophile. Now electrons will move from the carbon-hydrogen bond to restore the delocalized ring. So we show that with an arrow from the CH bond going into the positive charge. That will then release H+, and that H+ will react with AlCl4-, where a pair of electrons goes towards the hydrogen to then reform our catalyst AlCl3 and our hydrogen chloride. Alternatively, you could show that in the step before by showing the electrons on the negatively charged chloride ion going towards that hydrogen. The reaction conditions for this are quite simple. We should absolutely want anhydrous conditions, and we should probably do this in a fume cupboard. Anhydrous because we want AlCl3 to not react with water, because when it reacts with water, it reacts violently. And the fume cupboard is to mitigate the effects of this toxic hydrogen chloride. We also want to do this in the presence of AlCl3. Friedel-Kraft's acylation. For Friedel-Kraft's acylation, we want to know the overall equation, the mechanism, the conditions, and the equation for the formation of the electrophile. I know that this acylation involves the production of an acyl benzene, so I'll definitely need an acyl chloride for this reaction. And we're also going to produce HCl as a result of this reaction. I also know that benzene is unable to form electrophiles, so we definitely need a catalyst to react to form an electrophile. So we're going to use aluminium chloride. AlCl3 and acyl chloride react together, and that AlCl3 will gain a chloride ion to form AlCl4-. That also leaves us with a positively charged acyl group being formed, where the positive charge lies on that carbon atom. 2 electrons from the delocalized ring are used to form a bond with the acyl electrophile. So we draw our arrow going from delocalized ring, and I draw it going through the carbon atom and into that positively charged carbon atom in the acyl electrophile. This will cause a positive charge to be gained by the benzene and causes the delocalized ring to be disrupted. We show this once again by drawing a horseshoe shape around the carbon atom which formed the bond to the acyl, and we give that a positive charge. We also show the bonds to hydrogen and the bonds to that acyl group. Electrons will then move from the CH bond to restore that delocalized ring. So we show that with an arrow from the CH bond going into the positive charge. That will then produce our acyl chloride and release H+. And that H+ will receive electrons from the negatively charged chloride ion to then reform AlCl3 and HCl. Alternatively, you can show that in the prior step by showing the electrons from that chloride ion going to the hydrogen. The conditions for this are quite simple. We absolutely want anhydrous conditions, and we should probably do this in a fume cupboard. We want this to be anhydrous because AlCl3 will react violently with water, and a fume cupboard is used to then mitigate the effects of toxic hydrogen chloride produced. And we also want to do this in the presence of AlCl3. Phenols. Firstly, let's establish the property of phenols. Now, phenols are more reactive than benzene. That's because they are more susceptible to electrophilic attack. The reason it's more susceptible to electrophilic attack is because that lone pair of electrons on oxygen are incorporated into the ring of delocalized electrons. That reduces electron density on oxygen and increases electron density on the delocalized ring. And because that delocalized ring has higher electron density, it can therefore repel electrons in other substances to establish electrophiles, which it can then react. OH attached to the benzene ring in phenol acts as an activating group. So what that means is the second, fourth, and sixth carbon atoms in the ring are susceptible to an electrophilic attack. So any additional groups reacting with phenol will be redirected to those 3 carbon atoms specifically. So take the example of phenol and dilute nitric acid. The nitronium ion, the electrophile, will be redirected specifically to that 2nd, 4th and 6th carbon ring. So the product would look a bit like this, where there is NO2 only on the 2nd, 4th and 6th carbons in the ring, not the 3rd and not the 5th. You don't need to know why for A-level exams, it's beyond the requirements. However, that lone pair of electrons in the oxygen atom of OH causes electron density to be boosted on those specific carbon atoms because of an effect called resonance. And that's why those atoms are more susceptible to electrophilic attack. Phenol has a high boiling point, and that's because obviously that lone pair on oxygen can form hydrogen bonds, and we know that hydrogen bonds are a very strong intermolecular force of attraction, which requires a lot of energy to break. Now, phenols are also slightly soluble in water, and that's because that OH group can form hydrogen bonds with water because like dissolves like, that hydrophobic benzene ring, which obviously can't form hydrogen bonds, can't have water molecules pack around. So that's why we say phenol is only slightly soluble. Phenol can act as an acid, but it can only act as a weak acid. That's because there's only partial dissociation to form the conjugate base phenoxide and H+. And that phenoxide ion, that conjugate base, is a stable ion. So that's why we say it's a weak acid. But phenol as an acid is weaker than carboxylic acid. The phenoxide ion is stable, but it's less stable than a carboxylate ion. The reason for this is due to spreading of the negative charge in carboxylate. In carboxylate, we have this CO, which is an electron withdrawing group. So this charge is spread across the 2 oxygen atoms in a pi system. Now, in phenoxide, that benzene ring is also electron withdrawing. So the charge is spread out. With lower electronegativity carbon atoms. Key part of that though is the carbon atoms are lower in electronegativity. So that negative charge still lies more towards the oxygen because those carbon atoms can't pull that negative charge as well. So in phenoxide, charge is actually spread less than in carboxylate. And so that's why we say that phenoxide is less stable than carboxylate because there was greater spreading in the charge in that carboxylate ion. So phenol is going to be that weaker acid. Producing phenols requires multiple steps. Our first step is producing one of the reactants, nitrous acid, HNO2. It's an incredibly unstable and reactive species which needs to be made in situ. We produce nitric acid by reacting sodium nitrite with dilute HCl, and that will produce nitrous acid and NaCl. But because that nitrous acid is so unstable, we place ice into the solution, and that's to keep the temperature below 5 degrees. And that prevents the unstable nitrous acid from thermally decomposing. It involves producing a diazonium salt. That diazonium salt will then be used to produce phenol. Diazonium salts are used to get around the resistance of benzene to nucleophilic substitution. So we react the nitrous acid we have produced with phenylamine and more dilute hydrochloric acid to break nitrous acid into a nitrosonium ion. And then the reaction mechanism plays out. Eventually, we form benzene diazonium chloride, where a positive charge lays on this nitrogen atom, and there's a negative charge on the chloride ion. And we'll also produce water as well. Now, overall, we do this reaction again in the presence of ice, because that's going to lower the temperature below 5 degrees, and in doing so we prevent any unnecessary thermal decomposition of nitrous acid, and will also prevent any decomposition of the diazonium salt, which is unwanted right now. Now, benzene diazonium chloride, and all diazonium salts to be frank, are incredibly unstable and will readily decompose with temperatures over 10 degrees. So in our next step, we use that to our advantage. And we will heat the diazonium salt in the presence of water to then decompose that salt to form phenol, hydrogen chloride, and nitrogen.